series of the online seminar on optimization. It is my great honor, my great pleasure to welcome Boris Polyak as a speaker today. He is one of the huge names, great experts in optimization, with amazing contributions. He's a member of the Russian Academy of Sciences, and he's working on optimization topics, but also on control topics. His name was mentioned several times in the last weeks or during the seminar. So, and in connection to different topics, like was mentioned by Yuri Nesterov, in connection to Kubernetes regularization. Then Boris Polyak was mentioned in a talk by Aris Danielidis, related to the Leasevi's property, sometimes called Polyak-Leasevi's property. So Boris Polyak introduced the inertial methods. It's a long time ago. So amazing contributions. Thank you for accepting our invitation. So the talk today will be, again, between control and optimization. So the stage is yours.
Thanks, Rado, for your high assessment of my achievements. Thank you. And it is really a great pleasure for me to give this talk and to see so many faces of my old friends here, and also many young faces which are known for me. It is exciting. Okay, so my talk today will be on some links between control and optimization. So what I mean, first of all, it is a joint talk with my colleagues from the Institute for Control Science from Moscow, Ilyas Fathulin, Pavel Sherbakov, Mikhail Khlebnikov, and sorry, what happened? So what are the goals of my talk now? First of all, to demonstrate some close links between control and optimization, and to demonstrate some novel problems arising in this connection, and these problems are pretty non-standard. For instance, they are non-convex. We can adjust, we can modify standard minimization methods for these problems. And the most important, that there are a lot of extensions and real-life applications of these problems. So let me start with the simplest problem, which is called cornerstone of linear control. It is a linear quadratic regulator problem. So we have state X, control U, and the state is described by ordinary differential equation with some initial conditions. And our goal is to choose control U as a function of t in such way that to minimize this quadratic objective function. For simplicity, we assume that the matrices Q and R are positive definite, and the pair AB is controllable. That is, we can get from any point of the state to another with some control U. Well, it is the famous problem, as I said, and it was stated and solved by Kalman as early as in 1960. And the result was that optimal control has the form of static linear feedback of the state. This gain, optimal gain K, which is stationary, doesn't depend on T, is expressed in this form, where matrix, a positive definite matrix X is a solution of algebraic Riccati equation of this form. Okay, actually it is not completely explicit solution because algebraic Riccati equations has no formula for its solution, but there are numerous methods for recurrent methods for solution of Riccati equation. Okay, so all this stuff is well known, but let's look at this problem from slightly different point of view and look at it as a problem of feedback of this gain K optimization. So we have a function of this gain, which is quadratic now, where X is described by this closed form ordinary differential equation. So when we fix K, we can solve this equation, substitute it in this integral and calculate our function. Also, we assume that some stabilizing feedback is known. I mean, stabilizing that this closed loop matrix AK is Hurwitz stable. Okay, so now we have a problem of minimization of some function of K. Well, it is not completely explicitly written because we have this integral. So there are some important tools how to deal with such problems. The first one is Lyapunov lemma, then Lyapunov equation of this form has a positive definite solution if for a positive definite right-hand side, if and only if matrix A is Hurwitz. The second tool is Bellman lemma that if matrix A in this linear differential equation is Hurwitz, then we have expression for this quadratic, this integral of quadratic function of X. And it is equal to this quadratic form. X0 is initial condition, while positive definite X is a solution of Lyapunov equation with this matrix W in right-hand side. Okay, and the next minor technique is, well, instead of dealing with one initial condition, we can assume there is a set of initial conditions. Well, for instance, they are random, and we average all these initial conditions, and we have covariance matrix for this initial conditions equal to sigma. Okay, after this transformations, and we can get our optimization problem in the following form. Our objective function is equal trace of x times sigma, and we should minimize it. While this x is a solution of this equality matrix equality, and we assume, well, it's well defined only for those k which are stabilizing, that is matrix A minus BK Hurwitz stable. So, okay, we have more or less full description of our matrix optimization problem. We minimize this term subject to equality type constraints. And our goal is to apply some iterative methods like gradient-like methods for minimization of this function. Okay. So first of all, some references. Actually, Kalman himself also had this point of view on the problem. And for instance, he, in his pioneering paper, one can find the formulas for gradient of this function, f of k. And this approach was used by Levin and Athens at 1970 in their famous paper, where they proposed exactly the gradient method for minimization, and even for more general problems for so-called static output feedback. I'll say about it later. And there were many other works in this field, but all of them, they proposed the gradient-like method, but with no validation of this, with no results on convergence, local or global, and so on. And actually the breakthrough was this paper by Fazel, Gekakade, and Mesbachi in 2018 for not continuous time, but for discrete time problem. They got theorems on global convergence of the gradient method, and this was continued in this paper. And these three papers relate to continuous time case. I'll tell about these results a little bit later. Okay, so what? First of all, let's understand what kind of functions we work with. For instance, for the simplest case of one-dimensional state and one-dimensional control, we have explicit expression of this function, and it's k plus 1 over k. So you see, first of all, that the set of stabilizing controllers is unbounded. In this case, it's an array. And f of k grows dramatically near the boundary of this set. Okay, next example, well, it's three-dimensional state, one-dimensional control. And again, we see, in this case, we see that the domain of our function is non-convex. And this is a similar example of two-dimensional. And again, we meet non-convex domain of the function. So of course, the function itself is non-convex. And so let us prove what is possible about properties of our objective f of k and its domain S. First of all, it is a connected set. And sub-level set, which I introduced, the set S itself, this domain and sub-level set, they are both connected. And how it can be easily proved if we make some change of variables, and the initial problem can be reduced to a convex problem, and then we conclude the continuous image of the convex set is connected, and so it is okay. So there is such trick as change of variables, which allows to rewrite our optimization problem in new variables, semi-definite program. That is the convex optimization problem. But and it is done, for instance, in this paper, but it is impossible to do for other problems of this sort, and so we avoid this trick and deal with original variables. So the second statement is that function is coercive, that is, it tends to infinity when approaching the boundary and approaching the infinity. Okay. We have seen that the domain of f of k is unbounded, but sublevel, any sublevel set is bounded. It's very important. The next step is calculation of the gradient. Here are explicit formulas for the gradient. So how we can solve it? First, we find the matrix X, which was written when we fix k, there is Lyapunov equation for X. We solve it and find X. Next, here it is. Next, we solve this equation with relation to matrix Y, and find this positive definite Y. And here is the expression of the gradient. As I said, it is obtained by Kalman himself. And from these formulas, we can conclude that there is a point where gradient equals to 0, stationary point. It is the unique point. This is actually, it can be transformed to algebraic Riccati equation. This equation. Okay. Now, the second derivatives of f are also available. Well, it's complicated construction of the second derivative of matrix function. So we just calculate second derivative, directional second derivative, and it's given by these formulas. And again, what should be done to calculate this second derivative? It is just to solve some additional Lyapunov equation. And very important thing is that our function is L smooth. That is, but it's L smooth not on the all domain, but on any sublevel set. And the constant L depends on this value of f of k no 0. For instance, in our one-dimensional example, the function has this form. The second derivative is that one, and definitely it's not it's unbounded on for positive k. So it's the function is not L smooth on the entire domain. Okay. And the most important thing is that gradient domination condition holds for such functions. Well, we see they are non-convex, unbounded, and so on, but nevertheless, this condition holds true. Gradient domination condition, it's sometimes called Polyak-Loyasevich condition, but I would say that it's fair to call it Lezhansky-Polyak-Loyasevich condition because all three authors introduced this notion in 1963. Okay, roughly speaking, this condition claims that when gradient is small enough that our function is close to its minimal value. And moreover, our function, well, it's not convex, but it's locally in the neighborhood of the minimum point, it's strongly convex. Okay. Now we proceed to minimization methods. First, we can try continuous time gradient method. Well, it's the implementation of it is hard enough because we should solve two Lyapunov equations for every moment t. So we should solve continuous Lyapunov equations in continuous time, but forget about it and proceed to standard gradient descent. Okay, first of all, what can be said that, of course, we should pay much attention how to choose this step size, because the next gain k should be stabilizing, first of all. Then we need monotonicity in F, and also we can require some stronger condition, Armeyhol-like condition. I don't go into details here, but indeed such algorithms can be implemented. And the main point is that our function is L smooth, and then for small step sizes, gamma, we can guarantee all these properties. So actually, a rigorous algorithm of this form can be easily written, and due to this gradient dominant conditions, we can guarantee that we have convergence to the optimal regulator and its linear rate convergence. Okay. But now let's take some other choices for step size. Let's look for general unconstrained minimization problem in n-dimensional space. Let's choose step size gamma in this way. So what is this? It's actually a Newton method of one-dimensional minimization over gamma. And if our objective is quadratic, then this just is the method of steepest descent, which is well known to be convergent. And it can be proved that it's a function if L smooth and mu strongly convex, then the method locally converges, while for its damped version, when we have some damping factor here, it converges globally. Okay, so for our case, this method looks very suitable because, as we said, the calculation of directional second derivative requires just one more Lyapunov, solving of one more Lyapunov equation. And it's easy. And also, what happens when we are not in the neighborhood of minimum point, not in mu strongless neighborhood, but on the near the boundary, for instance, what we see that we leave the boundary fast enough. If we start with some small at zero, so it's this method is well suited for our goals. Also, we can adjust in the same manner the conjugate gradient method. We instead of one-dimensional minimization over alpha as in conjugate gradient, we write this explicit formula for alpha. Okay, so it looks good. Just a minute. Here is the result of simulation, and this is random data. Matrices state is 50, dimension of state 50, dimension of control 10. We start with A, which is Horowitz stable, so initial K0 is stabilizing. And here are three methods. One, this yellow, it is for gradient method with reducing step sizes. This is gradient descent with the special gamma formula, and this one is conjugate gradient. You see, it converges pretty fast. For these problems are not well. It is medium dimension, but well, 150 iterations are enough to find very the solution with high accuracy. Okay, and one more comment. Actually, we are in the framework of this problem. We have some equality time constraints and functions to be minimized. And actually, this equality, they have two groups of variables, and we can find solution x for any fixed y. Then we can substitute this x into our function, and we get unconstrained minimization problem. It's then we can write a gradient method for this function. It is so-called reduced gradient method proposed by Phil Wolf in 1968. So, well, what is new that you, as you have seen, we got some global convergence results for our problems, and there were no global global convergence result for this general framework of reduced gradient. Probably it can be achieved for some other kind of problems. Okay, so it was about continuous time, but as I said, there are no problems to extend it to discrete time problems. Well, I was talking about infinite horizon case when we had the integral from 0 to infinity, but also finite horizon case can be considered. And there are many open problems about implementation issues, how to solve large-scale problems, and so on. But all this is possible. Now, well, of course, this is not that important. Another way to solve linear quadratic regulator problems, but in many applications we deal. For instance, in so-called MPC, model predictive control, we deal with quadratic approximation at each stage, and it's important to solve it maybe not very accurate way, but fast, and this approach can be used in this. And finally, well, I believe there is some link between this type of functions and so-called relatively smooth functions, which we introduced recently by Lou, Friend, and Nesterov, and independently by Bauschke, Baltei, Mark de Boule in 2017. But actually, at this moment, I cannot embed it in this framework of this relative smooth function. Maybe it's possible in the future. Okay. Now we proceed to some extensions. And first of all, let's look at the problems where right-hand side matrix K depends on some scalar variables, M scalar variables K. And our goal is to choose these variables K in such way that to minimize this quadratic integral term, plus some penalty for large controls. And well, so What are the examples of such problems? First of all, it is so-called static output feedback. Static output feedback, it is a situation when we have no control, no state X available, but just some linear output Y. And we can try to find control as a function of the linear function of this output. Then we have deal with closed loop matrices of this form. And actually, this problem is particular case of what was written above. The next example is so-called decentralized control, when we deal with state feedback. But now we are limited with some linear subspace of stabilizing controllers. For instance, we need some entries of K to be zeros. It's very active field of research now. And well, the most intriguing application is PID controllers. PID controllers are the most widely used in practice type of controllers, and how to tune there are three coefficients there, and how to tune these coefficients to optimize some properties of our function. It's the problem. Okay, now if we with the same technique as above, we rewrite our problem, we obtain the objective function of this sort, where matrix P is the solution of Lyapunov equation, and also what is needed to have this matrix Hurwitz stable. And we assume also that some initial K0, which is stabilizing, is known. Okay, so it's now the problem of the well, now about the properties of this fund. There are, well, some of them are similar and some are dramatically different from functions mentioned above. Here, for instance, for one-dimensional control, we easily can get an objective function of this sort. You see it has two local minima. Moreover, in this example, we have disconnected domain. And here is an example of decentralized control. It's a very interesting example by Fenk and Lavey. Here is the matrix 4 by 4, but the similar example can be organized for n by n matrix. And well, the analysis shows that stability domain for these parameters has 2 times 2 power n minus 1 connectivity component. So the set of optimized stabilizing controllers for decentralized control is can be very disconnected. But sometimes some properties are good enough. We have the same coercivity problem. We have statement that sub-level sets are bounded. And also we can calculate first and second derivatives. I don't go into details here. There are formulas which require just solving more and more Lyapunov equations. And the main property again is that our function is L-smooth on sub-level set. But unfortunately, the most attractive property of gradient domination now it is lacking. So what the algorithm? Well, it's gradient distant again, but also we can add here coordinate distant. And again, I say for smart versions of this algorithms, we can guarantee monotonicity and convergence to stationary point, not to local or global minimum, but to stationary point. Maybe it's probable that we have convergence to local minima in most cases. Here is the example of lower controls. It's funny that this example has been analyzed in 1967 by Alexander Krasovsky. So we have 3x3 matrix, and we have two parameters here. And we want to adjust them to minimize quadratic function. And here is, well, this green line is the convergence of gradient method for this two parameter case. And well, this red one is LQR. Of course, by using LQR, that's when we have state variables available. So only we can achieve better results for the function, but you see the convergence is faster for when the number of variables gains is smaller. And for this case, for instance, if you look at the transient response, that is the output, we see that without control, it is pretty oscillating, and for two kinds, for LQR and for these two parameters approach, the transient response is more or less similar. Okay, now one can say that, well, but unfortunately here you can meet local minima and so on, but actually the experience of calculations demonstrate that fears of global optimization for this kind of problems is strongly exaggerated. And actually, well, in this kind of problems, we are not looking for global minima. We have some initial controller, initial regulator, and we just want to improve it as much as possible, but not to find something absolutely different. So maybe the situation is the same as in machine learning. In machine learning, people also said, well, these functions are non-convex, how we will deal with them and so on. But now nobody mentions these problems. Well, they solve machine learning problems, and that's okay. Okay. And now, very briefly about some further extensions. For instance, when we deal not with quadratic, but with other objective functions, when we work with not matrix equalities, but with inequalities, and how to apply some linearization methods for these problems, and also the problems with disturbances. Okay, very briefly about it. For first about well, we dealt with continuous times problems. Let's for just for fun to deal with discrete time systems. So we have simplest discrete time systems. A is a matrix, and A is a sure stable matrix. But so, but what happens if how large can be norm of xk maximized over k and over all initial conditions of norm 1? And it's the same to maximize the power ak, norm of power ak over k. Now, it's hard enough to calculate this quantity, but there is a simple upper bound for it. And the upper bound is the following. Let's solve this semi-definite program. So we have LMI constraints with respect to Q and minimize the norm of Q. That's convex problem, you know. Then the square root of norm of Q, optimal Q, is the upper bound for this quantity. And well, it can be proved by if we introduce Lyapunov function, quadratic Lyapunov function, and take invariant ellipsoid. All xk's remain in this invariant ellipsoid, provided x0 are in this ellipsoid. Okay. Now, assume we want to reduce this peak by use of state feedback. Yeah. So we have control, and the control is taken in this form, and then we can minimize the upper bound for this matrix, minimize over k, and well, actually it can be converted to convex problem, but we for more general case, when we have output, our problem is now the following. And it is static output feedback, and we want to minimize the peak effect for our closed loop system. And the upper bound is the following. We solve this problem, and then upper bound is square root of gamma. Okay. But so we see it's non-linear. Now it is matrix inequality, but it's strongly non-linear in K and P. So how to solve it? Well, we can just use, instead of gradient method, we can use more general form of it. It's trust region-like method. We are at some point pk, and we have some deviations, delta p, delta k. We linearize our nonlinear matrix inequality. This and now new variables are delta p and delta k. We have some restrictions for them, and we solve the minimization problem with all these constraints with respect to delta p and delta k. Okay, here is the, well, I don't have much rigorous results on these methods, but look how it works. It's a funny example. I mean, here is the matrix. Well, it's definitely, it's sure stable. Its spectral radius is smaller than one, but not very close to one. Norm is not large enough, but the peak is very large. It's 10 to 5. And what is interesting, it's achieved after many, many iterations, 141. Upper bound is close enough to this peak. And okay, so now let's try to vary just this term and to minimize over this k. And well, now you see this upper bound becomes much, much smaller. And the convergence is fast enough, 8 iterations. Okay. So, as I said, rigorous validations of all these approaches remains open problem. And one more, the last one problem. It's, well, until now, we had control problem with no disturbances. Now we assume there are some disturbances here. Well, if W is stochastic, well, there are no problems in Gaussian, then it's well known so-called LQG, linear quadratic Gaussian problem. It can be solved with no problems. But assume that disturbances are just bounded, but not non-random. And well, we have this constraint for all disturbances. Then again, by technique of invariant ellipsoid, well, invariant ellipsoid, we want to all these perturbs states remain in an ellipsoid and so on. We arrived at the following optimization problem. We minimize some, our variable is k and q, and we minimize this function with respect subject to nonlinear matrix inequality. Okay, now let's consider a slightly different form of trust region method. It's so-called linearization method, which was proposed. As far as I know, it's the first one who proposed this method was Boris Polyak in 1970. Then it was used, proposed by Steve Robinson, Han, and many others. Okay. The idea is very simple. We linearize our objective, we and linearize inequalities, and then we get something. Well, we have these penalty terms for deviations of our parameters, and we get something like this. So these are convex optimization problems with respect to delta k, delta q, delta alpha, and so on. And how it works for the pendulum. It is a double inverted pendulum when we can control this point, and perturbation is applied at this point. We have this set of differential equations. Perturbation is bounded. And we can use, for instance, for simplicity, state feedback. And we have some output we want to minimize. What we do want to minimize? We want to minimize some output. In our case, it's the first component and control. So they simultaneously should be small enough. And well, here is the result. The method converts, linearization method converts very fast in 20 iterations and so on. So now I conclude. So you see there's a relatively known bunch of non-convex smooth optimization problems related to static feedback and control. In some cases, we can get rigorous validations of the algorithms, but there are other cases where it remains an open problem. But in all cases, the results of simulations are promising. And the last thing that, well, it seems to me that it's a challenging new field for research. And actually, it's a very active field of research now, but not in optimization community, I would say, but in a community of people from control, from machine learning, and so on. And partially my goal was to attract the interest of optimization community to this sort of problems. Okay, thank you, that's all.
Thank you very much. Great talk. Indeed, emphasizing the importance of optimization techniques for this nice field of control, an important field of control, where, of course, the Russian school has a great tradition. So, yeah, it's a very, very nice talk, and proposing new interesting topics. Yeah, so it's time for questions. Yeah, then let me ask the first question. So in the second part, where the gradient domination property was missing,
yeah.
So then I guess that so of course, so the aim was not to converge to a global optimum, but then I guess that the convergence there is only along subsequences. Or is there a, since this is missing, I guess that the whole sequence is not converging. There is no global convergence.
No, the sequence of, well, we have no jumps between connected, disconnected components. We have the whole sequence is converging, but mostly it's to local minima, not well, we have no guarantee that it converges to global one, but the entire sequence converges.
Oh, despite of this missing Polyak service property.
Mm-hmm.
Yes, since I mean one of the features of this property is that it ensures global convergence and linear convergence rate.
Yeah, linear rate, yeah.
Okay, so but the whole sequence is converging. Okay, great. So other questions?
Radu, Maybe I had
Hi,
a
Patrick.
historical question for Boris. So, hi, Boris.
Hi,
You mentioned the PL inequality should be called LPL. And you said the first L should be for Legendre, actually?
Lezansky.
Ah, Lezansky, okay, I see. Because, yeah, because you mentioned 63, okay. All right.
Yeah,
And this was in the Russian literature?
No, it was a Polish researcher, and it's not widely known. I just found it recently when working. I found this old paper by Lezansky. Well, there were some other reasons to look at it, and it was a surprise to see that, well, the same condition is there, and it's the same year, 1963. Actually, there are some other his papers by Lezansky, but they were not available for me. I couldn't find. Well, there are some references in his papers for this older previous papers, but they are, as far as I understand, they are not available now in internet.
Okay, thank you.
Thank you, Patrick. So, other questions? So then I have a further question, this time related to the first part. So at some point where you use the gradient method, you mentioned that one issue is to guarantee that the new iterate is in the set S0. Okay? So this was, I mean, this can be done. But then the question is, wouldn't be not better to combine this gradient step with the projection step to project on the set S0?
It is. It's another opportunity. We didn't try it, but
Okay.
it's possible.
Possible.
Yeah, possible approach. Yeah.
Yes. And okay, so then I would have a further question. So in your method, so what you actually do in every step is solving the Lyapunov equation. How expensive is this? Is this expensive?
You know, it's not very expensive, but what is important, actually, that at each iteration we solve new Lyapunov equation, which is close enough to the previous one. And there are some techniques how if we have a solution of one Lyapunov equation, well, forget about Lyapunov, just a linear algebraic equation, and then we solve some close one with some small perturbations. Then we can get the solution having the initial point as initial point the previous approximation. Probably it's much cheaper.
Okay, great, thank you. So we have a question by Professor Forbes. Please ask your question.
Hi there. Thanks for the really great talk. I really enjoyed it. It was really wonderful combining or exploring the connections between optimization and control. I just have more of a comment actually, and I really agreed with what you said about you're not necessarily looking for a global optimal solution. You're generally looking for a better solution. And I believe that was in the context of a reduced order or a decoupled or decentralized control scheme. And I think that's a really important point that is sometimes lost on, in particular, reviewers, where I'm sure many of us in the control field have presented a solution where you can't guarantee global optimality, but it's better than anything you can hand tune. And in particular, when you're dealing with large scale systems, where you have maybe hundreds of design parameters, this hand tuning is not an option, right? So I really appreciated that point, which I think is really important to understand, is that in practical problems, you don't actually care about global optimality. You just care about a solution that works, that satisfies constraints, and that is in some sense optimal. So I really appreciate that. That's really my only comment. So thank you so much for mentioning that.
Thank you, James, for this report. Yeah, that's a very important point of view. Well, actually, I don't say that, well, forget about global optimizations and so on. No, but there are many situations when well, we don't care about global optima. It's not a well, enough is enough. So let's
wrong. If you can find a global solution, that's phenomenal. Like that's amazing. It's just as you said, like sometimes enough is enough, right? And sometimes like a practitioner just needs something that works, and they don't necessarily care about global optimality. So I think I think we all need to realize like what's the end game here. If your end game is yes, I need to prove, or I want to prove, or there's a really good reason to have a global solution, then by all means, like that's amazing, that's wonderful. But sometimes it's just not tractable, and a suboptimal solution might be just like better than nothing, right? So
sure.
Thank you. So we have a further question. So 16, do you want to ask a question, or should I read it? So so 16 is asking if the non-smoothness aspect is important in these problems. I mean, actually, yeah. So I'm not confused. Since actually, yeah, the setting was smooth. I'm not sure. Yeah, what do you mean by non-smoothness? Or probably the question is: are there any extensions here to the non-smooth setting? Are there any meaningful connect extensions?
Excuse me, there is something with sound now.
Okay, sorry. So we have a question which confused me a little bit. So, but I guess that yeah, our friend is asking if there are some extensions of these problems which are meaningful, but to non-smooth problem, non-differentiable problems.
I see. Well, you see, it is just the first step. Let's start with smooth, with differentiable problems, which are all of problems I deal with in this talk. They are smooth. Actually, of course, there are some non-smooth objectives in control, and they are of interest. But at the moment, I can say nothing about this possible extensions. Well, they are challenging, but it's the work of future.
Thank you very much. So I propose to stop here. Great talk. So thank you for proposing new interesting topics to the optimization community. So we enjoyed very much your talk. So we will just to say we will post the slides and the video on the website of the seminar.
Yeah, sure. I'll send them. Mm-hmm.
Thank you very much. So thank you for accepting our invitations. Thank you for this great talk. Thank you for answering our questions. Nice. I wish you all the best. I wish you a nice week. I just want to announce that our next speaker is Michael Friedlander, and that yeah, in Europe, yeah, we will change from summertime to winter time, yeah? And this might affect in some of in the countries you are the starting time of the seminar next Monday. So many thanks to Boris Polyak for a great talk, and all the best. Yeah? Stay healthy. See you next
See
week.
you. Mhm.
Thank you. Bye bye. See you.
Bye.